Okay, great. I believe we are now live. Let me actually drop a link to the interactive for today, which I think should be available. So the link in the chat should take you to an interactive. It's a very, very simple interactive, but it's something that you can play around with if you like. So today, for the most part, I want to focus on the main claim that is made in this chapter, which is what they call the ultimate Gilbreath principle, which I think is named so dramatically because it offers a complete characterization of all Gilbreath permutations. So, right. So I guess just to back up a little bit, let me tell you the plan for today. I think it's going to be a brief discussion because we don't have any effects for today. I actually mistakenly thought that there is a third trick based on Gilbreath in the book. Actually, what is there? I mean, there is a section called a little bit of magic in in the chapter, but what they actually do is a combination of Gilbreath and ideas from De Bruin, not in the sense that we have seen De Bruin before, but De Bruin worked on Gilbreath shuffles and ended up generalizing them a little bit. And I think the magic part of it is open ended. So I think they basically say that, okay, now that you have this extended Gilbreath property, can you put together a trick based on that? But unless I missed something, I don't think there is a concrete effect that's described. So the two things that we already saw, the first one, which was based on this lie detection with the help of a computer, the one that's what we saw day before yesterday, and the thing that we saw yesterday with dealing out two poker hands predictably all the time, and in fact even have the spectator do it, I think are the two main effects based on the Gilbreath principle in this book. However, as I think the authors also point out, the principle is very powerful and has been used to design many effects, sometimes in combination with other principles and sometimes with combined with sleet of hand and so on. And if you just do like a quick YouTube search for Gilbreath card magic, you will find um, a vast array of effects based on Gilbreath. But since uh, I want to constrain these discussions to what's in the book, so I'm not going to cover any of the any of those effects at least today, but we will instead try to focus on um, the main theorem, which still comes from the first part of the chapter. The second part of the chapter is this interesting connection um, with a certain collection of polynomials. So we'll come to that in a bit as well. But first, let's define what a Gilbreath permutation is. So imagine that you start with the identity permutation. So here 1 to 20, in general 1 to n, but in this interactive, this is 1 to 20. Right. So this is your original deck. I think of the leftmost card as being on the top of the deck and the rightmost card as being on the bottom. And then you start dealing out some of these cards, right? So, and thereby reversing their order. So let's say we deal out 8 of these cards, right? So as you can see on the red pile, which is the pile of cards that's being dealt out, one which was on the top of the original deck is now on the bottom, and then you just pile up the cards on top, and they show up in sequence. And then you do any valid riffle shuffle of these two decks. So if you click on this button, I don't know why, but in this implementation, the riffle's not particularly random, but yeah, you can riffle it a few times, and then you get this permutation of numbers that you see in gray. So any permutation of 1 to n that can be obtained by this procedure, which is to say to reverse, so start with identity, break it up into two parts, reverse one of the parts, and then do a riffle, right? Any permutation that can be obtained in such a fashion is called a Gilbreath permutation. So one first question to think about is how many Gilbreath permutations are there? Of course, the other question to think about is, given a permutation, can you determine if it's a Gilbreath permutation or not? right? So we'll come to the second question later. It's kind of what is characterized by that ultimate principle, which I will read off in just a bit. But maybe let's just take a minute to think about how do we count the number of Gilbert permutations, right? So I initially thought that they could be counted by encoding the stacks of the riffle in binaries. So this argument, just a heads up, is not quite right. Um, I was reverse engineering from the answer. So there's a passing remark in the book, which is justified later. There's a passing remark in the beginning where they say the number of Gilbert shuffles of order n is 2 to the n minus 1. So of course, so I was trying to force fit 2 to the n minus 1 somehow. So I figured that maybe you could think of labeling 1 to n with zeros and ones. So every run of zeros and ones that's broken up somewhere will give you the stacks of cards that are, that go together in the riffle. And if you complement the string, it's morally the same thing that happens. So maybe that's why it's 2 to the n minus 1. But I was puzzled because you can get, like, once you have a labeling of a string of length n with zeros and ones, you can still cut it anywhere. So it felt like the number should really be n minus 1 times 2 to the n minus 1, because n minus 1, or, well, let's see. Yeah, I think there are n minus 1 choices for, where to cut. And the reason this argument doesn't work is that not all binary strings are valid, correspond to valid riffles. Let me just demonstrate what I mean by this. Um, okay, there's a suggestion in the chat, which is along the lines of 20 choose 8. Do you mean once you decide to cut at 8, it's 20 choose 8? I see. Um, right, so that makes it sound like it might be a balls and bins kind of an argument. So once you have, like, that the blue cards are where they are, and now you need to make room for the red cards to kind of fall in place. So Sashi, you can shuffle. I mean, you can represent the shuffle in like whatever way you want, but it has to be a valid riffle in the sense that the main constraint is that the relative order of the blue cards and the relative order of the red cards is maintained. So what's going to happen is, if you imagine this is a physical deck, right? So depending on how you start letting go of the cards, some cards from the top deck will fall off. So let's look at what has happened in this riffle, right? So 1920, so we let go of 2 cards from the blue deck and then 1 card from the red deck. Then I think there was a run of 2 cards from the blue deck and 1 from the red, and so on. So, sorry, 2 from the red, 2, 3, then followed by 16. So that's 1. I should have, I think, I should have color coded the gray row as well. But anyway, the point is that the relative order of the 2 decks is maintained. So it's, in some sense, it's an interleaving, but it's an arbitrary interleaving, meaning that you can take as much as you can grab as many cards as you want from one deck before moving to the other one. So it's a bit like merge sort, except it isn't a meaningful merge. You can merge however you want. And now the question is, in how many ways can you merge, basically? So yeah, I think 20, right. So 20 choose 8 seems like close in spirit to what we want. Let me just think about. So okay, in some sense,
Shouldn't it be 20 minus 8 choose 8?
something like that. So here, right. So here, I guess, depending on what we want to. So let's look at the top row. We have, in some sense, we have um, 9 spaces, right? Below, you can go below the 1 and you can go above the 8. And on top of that,
along different lines. So let's say
hmm,
you have 20 gray spaces. So you are
right,
essentially choosing 8 places to keep the dealt cards. So
I see.
20 spaces and choose 8 dealt cards, and you place the dealt cards in those 8 boxes, and the rest remaining cards go in the remaining 12 boxes.
Correct. I think that sort of makes sense, right? So, Saraswati, if you look at it that way, you're basically picking, like, once you choose which positions are red and which positions are blue, the riffle gets determined because
Okay,
you're then
huh.
basically saying what will go where, right?
Right.
Yeah. Okay, so that seems like a legitimate argument. So I will not belabor my binary-based encoding argument because that was a little silly anyway. I don't know. I don't know what I was thinking really, but this makes sense. I think we basically want to figure out the positioning. Now, I guess if we do now, it's 20 choose 8. In general, it'll be n choose k, I guess. And you sum over you. So n is fixed. And what is the range of k? You can cut. I don't know if these. Yeah, so I guess I equals 1. You do want to deal off. I mean, technically, I guess this permutation is also a Gilbreath because you don't riffle anything off. And you're saying up to n by 2 because it's symmetric beyond this point, is it?
Is it symmetric?
Yeah, I'm also not completely sure. I'm thinking.
Mm.
You could take any of the set as dealt card and remaining cards, no?
Okay, okay, huh. No, but these cards are different.
Yeah, the
Oh,
numbers are.
yeah.
Yeah, so I don't know if we can derive once we have dealt off, let's say, 15 cards versus we've dealt off 5 cards. Like a permutation that we get out of this, for example, 6 will always follow 7. But here, when you have dealt off 15, I think 7 will follow 6. I mean, whatever. I think the order gets reversed. So I'm not sure that they are the same.
No, they are not the same.
Right? Yeah. So I'm not sure if we can mirror or like if there's a bijection between on either side of n by 2. But if we were to say n choose I for all I ranging from, yeah, because in particular, this other extreme where you deal off everything and you do an empty riffle, this is the opposite permutation from the one where you deal off nothing. So these are two distinct permutations. Um, so if
If
we,
we
if
take I equal to 0 to n, then it will become 2 to the power n.
2
Or
to the power n, correct.
mm,
Yeah. Yeah, that's the sum of all subsets. Um, that's 2 to the n. So I don't know if there's a reason to discard about half of them. It's not like it's not clear. Um,
So we may count for a fixed number of dealt cards. We can
mm,
count how many such possibilities are there, right? Let's say if dealt cards are I, then in that case
correct.
we can
So
count, then we can sum over all the I's, for example, maybe.
right, right. So I think that is yeah. So that's where I think we started. So here I think Pratik was suggesting that this is 20 choose 8, but among the 20 choose 8 possibilities, is there a reason to believe that? So what are we doing here? We are basically saying choose 8 positions among among the 20 final positions in the gray row. And in those 8 positions, the I want to dump the red cards, and their order is fixed. And in the remaining 20 minus 8, this remaining 12 positions, I want to dump all the blue cards. I don't know if there is. Of course, when we are in the special case where, so here this is forced. When I choose 10 positions, I don't know if I have an additional, I don't know if I have an additional piece of freedom because now I have chosen 10 positions. Those 10 positions can go to either red or blue. I don't know if that's just a matter of fixing a convention there. Um, yeah, we seem to have here a legitimate argument for why there should be 2 to the n Gilbreath shuffles. Um, Maybe it's worth working it out for like a really tiny number. I think in the book they're explicit about it for 4 or something. We don't have to do 4. We could instead do, let me just shorten this to, okay, maybe. So how much is, yeah, 3 seems manageable because it's either 8 or 4. We should be able to discover our symmetries. Yeah, so sorry, this is just the local version of this file. So this is 1, 2, 3. If we are to note, okay, where can 1 go in? So we get, okay, so 1, 2, 3 already is like a repeat of what we saw in the beginning. So it can either be 2, 3, 1 or 2, 1, 3. Those are the 2 new permutations, right? So 1 can either go in the middle of the deck in a riffle or it can go at the end. If it goes in the beginning, that's something we've seen before. So we record 2 new permutations from um, oh, Shashi's saying I should have taken 5. Yeah, I'm happy to do 5 right after this, but let's just figure it out. So for 3, the question is the answer 4 or 8? The claim is that it's 4. We seem to think it's 8. But already here, I think we would have said that for this, it's 3, choose 2 or 3. But instead, especially if we count this, yeah, if we count this, we don't, like for all the 3 choices, we don't get something new. Similarly here, so it's either a 3, 2, 1 or a 2, 3, 1 or a 2, 1, 3. If we count the 3, 2, 1 here, this is not meaningful.
3 to 1 repeats.
Sorry?
3 to 1 is repeating, right? Like if you see, if you
Yeah, 3 to
held
1
just
and
1
1
to 2,
2, correct. 3 to 1 and 1 to 3 are repeating, but it's
2, 1, 3 also.
2, 1, 3.
That also happened when we put 1 on one side and
Correct. 2, 1, 3 is repeating here and 2, 1, 3 is repeating here.
maybe there's an argument that everything repeats once again. So that's
Right,
why.
right. Yeah, that would be really nice to be able to say that we are overcounting exactly by a factor of 2. And yeah, maybe there is a certain symmetry to this in the sense that when you are plugging, okay, how did the 2, 3, 2, 1, 3 repeat? This was 1 going in the middle here versus 3 coming on the top here. Yeah, so the question is for any permutation that we see here at the bottom, is there a way of systematically generating it in using some other bucket? And
at least for the first kind of thing, I see that if we place the entire red,
correct.
no,
Yeah, for the first thing, I mean, 1, 2, 3, 4, I think this you can generate here easily, the first one. But if I have something like this, can I,
So the top card can actually be placed on any either of the dealt card or remaining card. You'll get a shuffle. So for example, if 5 was placed on the dealt card, you could still get this shuffle.
correct, when you move it up, right,
The top card, right? That
correct,
repeats. So
correct,
so in this case, let's say if you put 4 in the remaining cards, then you'll get
correct.
this. You can get the same shuffle.
You can
So
generate
that's
the same. I see.
so here in this case, 3, if you place the 3 on the remaining cards, then you
Correct.
could still generate this shuffle. So I think that way every shuffle has a pair where you swap
Correct.
whether dealt or remaining, and then I think that would be the argument.
Yeah, yeah, I think that does seem reasonable. So what we are basically saying is, yeah, let's look at this shuffle here. I think the point is that you could have also generated the shuffle, whatever the shuffle is. If you had dealt off one more card, this would have still been a valid thing in the old regime. And we have to argue nowhere else, in the sense that we have to argue that we are overcounting exactly by a factor of 2. And yeah, I'm more or less convinced that this makes sense. Like the fact that every permutation can be
So
captured by.
maybe we should argue like this.
Yes,
So in this one, with 5 going before 4,
correct.
there would be 20 choose 4, 5 something. And then with 4 going before 5, those will not be repeated when 5 is also dealt.
Right, with 4 going before 5 will probably be
No,
repeated
4 going
here.
before 5 cannot be coming if 5 is dealt in the shuffle.
Correct.
So all those with 5 going before 4,
Correct.
they will all be repeated.
They will all be repeated in the previous, like
Yeah.
here. Right. Yeah, so here I'm looking at 4 followed by 5 in the gray shuffle. And that's something that is a totally legitimate thing, even when 4 was not dealt out. But here it's also possible that 5 comes after 4, and that can happen if 5 was also dealt out, then 5 can come after 4. So I guess, and everything else you can anyway see. So no matter what permutation you have between, there's something going on between those top 2 cards, I think.
Another argument that I could think of is like if you look at a shuffle, right? And you could separate the increasing parts and decreasing parts. So increasing parts would become your remaining cards and decreasing with the dealt card. But the first card gets a choice. It could either be in the dealt card or in the remaining cards. Because if you put 5 in the remaining cards, it's still an increasing card. Or if you put 5 in the dealt card, it's still decreasing and increasing. So for the first card gets a freedom to be in either of the dealt or remaining cards, but the rest of them gets fixed, whether they form a decreasing pattern or an increasing pattern.
Correct. But this is still trying to justify that the overcounting is exactly by a factor of 2, right?
Yes.
Okay, right. Makes sense. Okay, sure. Yeah, I mean, I think I'm more or less convinced that it's basically what's going on at the place where the deck was cut is basically either you can go one before or one after to basically see that the same permutation will get generated one more time. And I think you can also argue that the same permutation will not get generated in any other bucket. This is the only overcounting that happens. So I think the official argument in the book is actually perhaps not very different. I mean, let me just see if I can. Okay.
Hold on. See, but in the current situation that you are showing.
Yeah. Sorry, I think I just pulled the screen share out, but let me go back to it. The situation here. Yeah.
See, 6, 5, 4 can happen here.
6, 5, 4. Yeah, the dealt cards can come like that. That's right.
And it can also come when 6 goes to the dealt card.
Correct.
And
but it cannot happen here, for example, because
yes, okay, sorry. I got confused in between. Earlier, whatever is saving is correct.
Right.
Sorry.
So yeah, it seems like this. Yeah, it's just like at the place where the deck is cut, you can either step back or step forward to see the same permutation again. So hopefully the overcounting factor is exactly 2. And actually that would be like, yeah, I think that would be a slightly different argument from the one presented in the book. I don't know if the two arguments are like morally equivalent. Let me let me just maybe briefly discuss what they have to say. So what they're saying is, let's consider the set 2, 3, 4 up to n. This writing is visible, right? I mean, I don't know if it's legible, but it's visible. Yeah, okay, great. So basically pick any subset of 2 to n. And what they're saying is basically these are, so maybe let's as an example, let's say n is equal to 5. So I have 2, 3, 4, 5. And let's say my subset is 3 and 5. So to build out a permutation of 1, 2, 3, 4, 5, right? So if we take a set of size 2, that basically means that we dealt off 2 cards. So what we're going to do is place, so j is the number of dealt off cards. So j is 2. So I'm going to put 2 and 1 in positions 3 and 5. That's what my set is telling me to do. So in positions 3 and 5, I'm going to place 2 and 1. And then the rest of it is basically going to get interleaved. So this is from...
So in this case, they are skipping 1. So that means they are fixing that top card to be from the remaining card.
Right. From... Yeah, let's... I think you're right. So... But I think the claim is still that you can generate... so if you want to generate a Gilbreath permutation, their point is the following, right? Basically, the delta of cards, I think maybe there's an implicit assumption that you're not dealing everything out, because again, that is something that you can generate it actually from the situation where, so when you deal everything out, the riffle just gives you, it's an empty riffle which gives you this permutation, right? Yeah, so I think mm,
This can be generated if we take the S as empty set.
can it be generated with S as empty set?
No, S as the whole set? No.
Yeah, you're right. Take S as the whole set. 2, 3, 4, 5. Yeah, exactly. So if S is the whole set, 2, 3, 4, 5, then the rule will say place 1, 2, 3, 4 in positions, well, 1, 2, 3, 4, but in reverse. So 4, 3, 2, 1. So I'm going to do, so let's say S is, there's another example now. So S is 2, 3, 4, and 5. So the rule is we're going to go 4, 3, 2, 1. And the only thing that remains is 5. So that's going to come here. So this can be generated. That's why they don't explicitly care about, I think, the situation where all, yeah, so like I said, because S is only 2 to n, even when you take everything, you can only generate like a subset of size n minus 1. So the question is, are they missing out in the situation where n cards are being dealt out? But they're not, because when n cards are being dealt out, the only permutation you can generate is this fully reversed permutation. But that's something that you can get if you picked S to be 2, 3, 4, 5. But I think here is the claim. The claim is that every Gilbreath permutation, let me just call that GP, can be generated by this procedure, by this process, by which I mean that the Gilbreath permutations are in one-to-one correspondence with a choice of subsets up to n. And the number of such subsets, of course, is 2 to the n minus 1. And thereby we are done. So let's just check this one-to-one correspondence. So if you give me a Gilbreath permutation, let's argue that there is a choice of S for which it would be true. So what's happening in Gilbreath is you have, let's say you choose to deal off some J cards. So what does that mean? It means you have 1, 2, 3 all the way up to J. And then here you have J plus 1 and so on to n minus 1n. So you're doing a riffle between these two. And this is like your 20 choose 8 argument, right? So these J cards are going to fall somewhere, okay? And they're going to fall into, so again, let's assume that we have not dealt off the whole deck because that's without loss of generality. Because like I said, like you just argued, if you deal off the whole deck, the unique Gilbreath permutation you get from that is the fully reversed permutation, which you can also generate by dealing off only one card. Sorry, by dealing off all but one card. So that's okay. It's sort of something that shows up. So without loss of generality, you have dealt off fewer than strictly less than n cards. These n cards are going to land up at some positions in the riffle. So just look at the positions that they land up in, okay, and pick S to be exactly that, right? Pick S to be exactly that, or pick S to be, I think pick. So essentially what we said was when you pick S, okay, this is, I think just to make this concrete. So place J in position 1, J minus, not position 1, but position S1, which is, so let's say your S is S1 to Sj. So J minus 1 in position S2, and so on. And 1 in position Sj. So you've dealt off J cards and their positioning is given to you by S. So so we are going in this direction that if there is a Gilbreath permutation, then there is a subset, there's a choice of a subset S for which we would actually end up generating that permutation. And if you give me a Gilbreath permutation, I'll basically ask you how many cards did you deal off and what did your riffle look like. So you'll tell me you dealt off J cards, and then after the riffle, my permutation looks like this. So I will go and find out where these J cards landed. I will read off their positions and I will say, okay, this is the position of J is my S1, the position of 1 is my Sj, right? So for that set, choice of that set, I would have basically generated your permutation using this procedure, using S. On the other hand, if we have a S, then the permutation that we get by following this procedure, which is where we are saying, let's look at, maybe let's just say there are 4 of these, and this is proof by example, sorry. So let's say these are our positions. So what we want to say is, okay, let's say we've fixed our S to be this set here. So 2, 3, 5, and so it didn't have to be like that, for example, maybe. Okay, so maybe this is my S. Actually, does it matter? This is an arbitrary subset as opposed to an ordered. Yeah, I think we just assume that S is an increasing order because that's otherwise I think this would not make sense. Sorry. Yeah, because I think I just realized this as I was writing this down. So let's say S is 2, 3, 5, 7. For the purposes of extracting a permutation out of S, I'm going to think of the positions as being okay, so S is an arbitrary subset. And we are going to write down the elements of this subset in increasing order. And what we want to do to generate this permutation is we are going to say, well, we have, I think, something like this. We're going to go 1, 2, 3, 4. And then for the interleaving, we're going to come back and say something like that. Does that make sense? That sort of basically says that in the riffle, remember, so our deck was like, I think we had 1, 2, 3, 4. And then it was still like 5 on the top. So I guess what happened was, if you think, I don't know how you prefer to think of riffles, bottom to top or top to bottom, but 8, 9 fell down from the left first, I guess. So 9 goes to the absolute bottom of the deck. So this side is the bottom. And this side is the top. So we pulled out 8 and 9 here. Actually, yeah. And then 1 from here. Then 7 from here. Then 2 from here. Then 6 from here. And 3 and 4 from here. And 5 from here. So if you were to write down a shuffle, if you were to write down a permutation according to this procedure, it can be realized by a Gilbreath.
Yeah, I may be missing something. Is there a reason why 4 cannot go on top of 5?
4 can go on top of 5. We'll just need a different set to realize that, I think.
What is that set?
Wouldn't it be like 1, 3?
But I thought S is a subset of 2, 3, and so on.
I see.
Book is avoiding the argument that we got into with our and choose to argument, right? They
Okay,
just
sorry.
the first one to be from the remaining deck. So that avoids that factor of 2.
That avoids the overcounting, but yeah, you're right. So to generate this permutation with our procedure, I think we would have to cut the deck at 3. So we would get it using a different set. I think I was too rushed to say it's going to be this. So let's say we want to generate this permutation. Let me get rid of the color coding because I don't want to imagine that the deck is stacked up this way. Yeah, this also makes explicit why this guy is not overcounting. So let's say this is the permutation that we want to generate. This is a valid Gilbreath permutation. So which set is going to bring us here? Let's see. We want to go 1, 2, 3. So, okay, so I think that's a good thing to make concrete. How do you determine the set from the permutation? So I guess we start with 1, 2, 3 and go as far ahead as we can to the left, avoiding the very first position, because I think this, as you're pointing out, is the thing that is overcounting. So now we have 1, 2, 3. Yeah, so this was the Gilbreath shuffle that generated this. You can think of this as, you can think of this again as 9 and 8, 1, 7, 2, 6, 3, and then 5 and 4. And the set in this case would therefore be 3, 5, and 7. Yeah, so I think there's definitely something slightly subtle going on here, which I'm probably.
So just go to the previous one that we did, which was 5, 4, 6.
Yeah, sure.
5, 4, 3, 6.
Yeah. Let me write that one down as well.
No, I think it's clear. I think 4. So every permutation here has one increasing up sequence and one decreasing sequence, right?
Exactly, right.
If you remember your longest common subsequence type thing, right?
Correct.
So this is essentially one sequence which is completely up and one is down. The 4 happens to belong to both.
Right. So you disambiguate by making the choice.
That's the reason why you're not picking up the 1.
Correct.
You force the 4 to be part of the one of them and not the other.
Correct.
So 4 is now part of the ascending sequence, not the descending sequence.
Correct. So even here, I think we avoid, we avoid getting into the 5, I guess, from the previous example. But yeah, here I think we could have gone all the way to the 4. 4 is also part of the decreasing sequence, like you pointed out. So, sorry, the increasing sequence. Yeah.
So, in our argument, look at the second one that you've written, that is 5, 4, 3, 6, 2, 7, 1, 8, 9.
Correct.
So if we dealt off 5, 4, 3, 2, 1, we could have got this. If we had dealt out 4, 3, 2, 1, then also we could have got
Correct.
this.
Correct.
And if we had dealt out 3, 2, 1, then also we could have got this.
No, I think no. 3 to 1
Yes.
would not. If 3 to 1 is there, then the sequence remaining would become 5, 4, 6, which is not increasing, right?
Okay, yes.
Right. So this 4, 5 would have gone down as 4, 5, I think. Yeah. With 3 to 1. Yeah. So I think it's basically the flip at the top. Like the question is this guy here. Yeah, the same sequence can be generated by dealing of either these many or one less, I guess. And I think that's captured as basically you have an ambiguity in, like, if you take the maximal increasing and the maximal decreasing sequences, then I think there will be an element that's common to both, as is happening here. So if I start off with basically, okay, let's just do the run from, so we're saying we start off with 1 and we follow along 2, 3, and 4. And you start off with, so that's whatever, that's increasing as you go to the left. And this is decreasing starting from 9, 8, 7, 6, 5, and 4. So I think what Vinay was saying is that 4 participates in both of those. And essentially, that's a question of deciding, are you imagining dealing out that extra card or not? So the same sequence can be obtained by a riffle of dealing of the top 5 or the top 4 cards. And to avoid that overcounting is why they're skipping 1 from this subset. So yeah, okay. So so I think the only thing I had realized when I looked at the argument in the book after my own failed attempts was to see that if such a S is given to us, what we get is a Gilbreath shuffle. But I think I not carefully considered the other direction, which basically ensures that the bijection, I mean, that these two things are indeed a bijection, that you have Gilbreath permutation is generated by a set S and a set, I mean, okay, if you fix a set S, you definitely get a Gilbreath permutation. Given a Gilbreath permutation, I think there are 2 possible sets that can generate it. So by knocking out the 1 is how we make sure that it's knocking out the top position is how we disambiguate and say that we are not overcounting. And that also makes the overcounting in the previous argument that we came up with, or you folks came up with in the chat, like, I think it makes it clear why it avoids the overcounting. Yeah. So I agree with Pratik's comment in the chat that the argument of saying that basically you're looking at n choose k for a cut, like when you have dealt of k cards, it's basically n choose k. But I think it's like, but then you account for the overcount. That argument and this argument that's presented in the book are probably like I think it's reasonable to say that they're morally equivalent. Okay, so so there's also like the ultimate Gilbreath principle, which also they give a proof of at the end of the chapter. I don't know if we will have time to necessarily go over the proof, but let's at least talk about what the principle is. I think maybe from the mechanics of the shuffle, it's at least perhaps most of the claims are kind of intuitive, but the more interesting, I think the far less obvious claim they make is about counting how many of these Gilbreath permutations are actually cyclic permutations, meaning that if you were to write it down, if you had to write it down in cycle notation, like let's say 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes to 5, etc., then you get only one cycle. So every permutation basically decomposes into one or more cycles. Cyclic permutations are the ones that have exactly one cycle in them. You basically just go around. And it turns out that roughly a 1 over n fraction of roughly 1 over n fraction of this 2 to the n minus 1 Gilbreath permutations happen to be cyclic. So it's also kind of, I think they have this really neat connection where they say that all these cyclic permutations are in 1-1 correspondence with a certain interpretation of the zeros of a certain polynomial. So that's a very surprising kind of a connection with polynomials. But I think before we get to that, let me just write out what the more basic this idea of the ultimate principle. I'm just debating if I should switch back to the well, you have the link to where you can play around with the riffles. So I will keep my iPad screen here. So here's the like the structural characterization. So pi is a Gilbreath permutation is equivalent to saying that for all j, if you look at the top k, the top j, so pi 1 through pi j, these guys are all distinct mod j. Okay, I will skip the third property. It's just a little annoying to write, but essentially what they're saying is if you kind of slide out this window, like not just the top j, but if you pick out if you pick out another j, like you take a sliding window, they continue to be distinct mod j. So we'll come back to that. But I think the easier, the more interesting thing is this. Yeah, okay, I don't mean to make a value judgment, but I thought this was really cute, the last one. The top j cards are consecutive in 1 to n. So I think this maybe requires a bit of an explanation. So the top j may not be consecutive when you read them out, but as a set, it's a consecutive subset of 1 to n. So let's again try and deal off some cards physically here. So maybe let's do this with n equals 9 or something. And let's say we do I didn't space this out very well, but again, this side is the top, this side is the bottom. Yeah, so when you riffle these in, so let's maybe write down one example of a Gilbreath outcome. I'm just going to make some space for myself. So okay, so let's okay, so essentially as you track like pull out any of these, right? Let's look at, in this case, the top 5. So we see 5, 4, 6, 7, 8. So essentially, if you reorder them, if you sort these numbers, you get 4, 5, 6, 7, 8, right? So there are no gaps. That's what this property is trying to say. So what we have right now is 4, 5, 6, 7, 8. If you look at the top, if you look at the top 5 guys, is sorted list, sorted partial list. So the next number will either be a 3 or it'll be a 9. Next number happens to be a 3. So the next number will either be a 2 or it'll be a 9. That's essentially what this is saying. So just look at the top, like cut off as much as you want. And you'll find, and again, just given the physical mechanics of the Gilbreath shuffle, maybe this is not It's not very surprising, perhaps, because um, yeah, let's look at what's going on from the top, right? So um, in the riffle, what would have happened is at some point you would have let go. Like if you think of, imagine that you do the riffle shuffle, you record it and play it backwards in slow motion. So look at which side landed up on the top. It's either going to be like the top deck or the bottom, like it's going to be either the left or the right. So let's say the top few cards, the top consecutive run comes from this part. So you would have dropped off, let's say at the end of the shuffle, maybe it would have been the top 3 cards from here. Then the next few cards must come from the top of the other side. But the top of the other side, because you have reversed the original order, right? So this portion is just picking up from where this guy left off. So you're kind of extending the list from the other side. And the rest is basically an extension of this argument. So whenever you drop off things from the left deck, you are extending to the higher numbers. And whenever you drop things from the right deck, you are extending on the other side. So you remain contiguous as a set. Of course, the ordering itself will be kind of random because you're riffling it in. But as a set of numbers, you're getting a contiguous subset of 1 to n. Is that yeah, sorry, I only have a proof by let's stare at it kind of a technique, but is that kind of clear? So Pratik's already commented that they will always be consecutive.
So this can be shown by induction also, no? Means whatever
Yeah, I
you
think,
said.
yeah, sure. I think you should be able to formalize it a little bit using induction, saying maybe, yeah, I think I was just lazy about saying induction on, I guess, the number of iterations of the riffle that you're doing, and depending on like which side of the deck the cards are falling from. But yeah, I think it's kind of visible that there is this interval which is kind of growing. The interval starts off in the middle of 1 to n. The middle is where, by middle, I just mean like it's not, of course, it may not be actually the middle, but essentially wherever you cut off the deck, at whatever J cards you cut off the deck. So it kind of starts growing from there, right? So maybe this is a bit easier to see with the simulation. So right. So here you see that you picked up a few from the top. And when you start picking things from the bottom, you're essentially extending on the higher side. And when you start, like I said, I really wish I'd color coded the gray row as well. But anyway, as you pull in more red cards, you are extending towards 1. And as you pull in more of the blue cards, you are extending towards n. You're starting off somewhere in the middle, and this just keeps going. Now, once you believe that the top J are consecutive, you also know that they must have, like, if I pick 5 consecutive numbers, they will have different remainders mod 5, right? Because they're 5 consecutive numbers. So that's so once you know this property, the the remainders modulo the window size being distinct also follows. And you probably can do some, yeah, I mean, and I don't know if this has I mean, I think the number file video, if I'm not wrong, probably gave some sort of a magical application of this. Yeah, I mean, so this is like a useful property to keep in mind to see if maybe you can rig some effects based on this fact. But it's also just like a nice patterny thing about these permutations. So what's interesting is, I think the claim in the book is that this is a characterization of Gilbreath permutations. So I think if you are consecutive, as the way I mean consecutive is not that it's literally consecutive, but interpret it as a set. It's a consecutive segment of 1 to n. So if you're consecutive for every J, every window J starting like anchored at the leftmost position, and for every J you're consecutive, well, this is true of Gilbreath permutations, but if you have a permutation of which this is true, it must be a Gilbreath permutation as well. And actually, that's not, I mean, I initially thought that was kind of surprising, but I think I mean, if somebody gives you a permutation where things are consecutive like that, but as a set, they're kind of maybe mixed up, you can basically, I think, try to, okay, I've not tried to actually prove this, but I think what you can do is take that consecutive set and see in what way it has been rearranged in that window. And from there, I think you can reverse engineer how the riffle must have looked for this particular pattern to emerge. So it's something that I think was kind of visible from examples. And if you,
May I try an argument?
yeah,
So if
absolutely.
you see that property is holding good in the dealt cards, and the
Correct.
property holds good in the remaining cards,
Correct.
and the extreme is that conjunction point, where
Correct.
again that is satisfied.
Right.
So once it's satisfied for the first interleaving,
Correct.
thereafter it is going to be satisfied.
Right, but this is, I think, going in the first direction where we are saying that if it's Gilbreath, then it'll have this property, right?
Yes.
Right. Correct. So that I think, yeah. So this I agree that I think if you yeah, they're consecutive in the individual decks. That's definitely helpful. And because of the splitting doing this, I mean, having the effect of this reversal, so this would not work if you just pulled up the deck and did a riffle, but because you're dealing off the cards and reversing the order, yeah, that's why as you do the riffle, it's exactly as you described. At the conjunction point, you're going to expand on either side. And I don't know if this merits being I mean, I think when Saraswati mentioned induction, it probably meant that you can use an induction framework to formalize the last part of what you said, that if it holds at the top, it'll hold at the rest. So basically, you look at the top.
Or you could treat it this way. Say, let's say when we have riffled, we have A1, A2, A3 chunks from the dealt cards,
Correct.
and B1, B2, B3, etc. from the remaining cards.
Right.
So that A1, A2, etc., they are all satisfying the property. B1, B2, etc. are satisfying the property.
Correct.
So once you bring A1 with B1 in some place, or it will be A1, A2, then B1.
Yeah, I mean, if you think of your AIs and BIs as maximal chunks, actually what you're saying makes it kind of clean,
Yes,
because I
yes.
think the last element of A1 will be consecutive with, like here, for example,
Yes,
you have 6,
yes.
5, 4 followed by a 7. So, so the first element of B1 and the first element of A1 are actually consecutive, and that's probably always true. So
Yeah, and that is enough. We
yeah,
don't
that
need
is
to go for induction.
correct. Yeah, I think that's correct. I think that's a one shot. Oops, sorry about that. So yeah, okay. So I guess we yeah, that's I think a complete argument. Look at the interleaving, identify the maximal chunks from both sides, label them AIs and BIs, and observe that the top of each chunk is those numbers are basically next to each other by construction, and I think that does it. And yeah, from the consecutive thing, you can infer also the distinct remainders mod window size. That also follows. That you can slide that window and it still works. I think there's a little bit of detail that I think I will declare as being out of scope, given that we are going to be now over the hour. There are a few other details in this chapter that are quite nice. So again, just to recap, we saw what Gilbreath permutations are. They are permutations that you can obtain in this particular you can define them by this physical mechanism, but now we also know that they can be characterized by this pattern, which basically says that if you look at J length if you look at J-length windows starting from the left and they're all continuous, then that's when you have a Gilbreath permutation. That's a nice structural characterization. I think what we just proved was that every Gilbreath permutation has the structure, and it turns out that the other direction is also true. If you have this structure, then I think you can lay over that AI-BI lens and reverse engineer what the riffle would have been to achieve this structure. So I think that also makes sense. So we know exactly what, I mean, yeah, we have a nice structural characterization of these permutations. We also know exactly how many there are. That's also interesting. They're like a nice closed form thing, 2 to the n minus 1. In the book, they also talk about how many of these are cyclic permutations. And like I said, they make a connection between like the set of cyclic Gilbreath permutations being in 1-1 correspondence with the zeros of a certain family of polynomials. So that's where, if you looked at the title of the chapter, they say from Gilbreath to Mandelbrot. So I think the reason Mandelbrot sets come in is because they talk about polynomials that can be generated through a recursive mechanism. And they talk about the zeros of these polynomials. And if you look at how the zeros are ordered in some sense, it turns out that those orderings give you something about cyclic Gilbreath permutation. So it's absolutely fascinating. They have some references to papers that talk about this connection, but they don't actually prove it or anything. But if you're interested, there's like a couple of pages that makes for a very nice reading. I think, again, mostly in the interest of time, I will probably not dig into this any further, but they also give, like I said, 3 other things that we will not go over. They give 2 non-magical applications of Gilbreath shuffles. For one, they cite Knuth and something to do with how things are stored on disk. And for the other one, they cite Penrose, and there's some nice connection with aperiodic Penrose stylings. So 2 reasonably versatile applications of these permutations. And like I mentioned in passing earlier, De Bruin shows up. They talk about a slightly different setting where you take 2 decks of equal size, and let's say one is alternating spades and diamonds, the other is alternating clubs and hearts or whatever, and then you riffle these in. So you have 26 cards on either side and you riffle these in. So this is special. Since it's a special case of a Gilbreath shuffle, it of course has the nice Gilbreath properties, but in Gilbreath, once you are done with the riffle, you are kind of done. You don't, as we discussed, I think either yesterday or day before, if you start cutting the deck after you do the riffle, you may lose the property that, for example, alternating red and black. If you give it an odd cut, the property may no longer hold. So if you start off with decks that are stacked up equally, De Bruin, I think, showed that you can give it a free cut anywhere you want, and you will have not necessarily an alternating, I mean, either you get alternating red-black, which is the original guarantee, or you get a combination of like a high card and a low card, like, which is, I think, a club and a heart, like, so you get something else with the suit. So I don't know if I'm recalling this perfectly, but basically with a free cut, you guarantee one of 2 things, but you pay a price for it, because I think in the setup now, in the original Gilbreath permutations, you could riffle, you could deal off any number of cards and riffle them. It didn't have to be half and half. Here, in the beginning, it has to be half and half, but after the riffle, you get a free cut and you still get some properties to be true. This is where I originally thought they also had a trick based on this, but they leave that open-ended, saying that maybe with these variations, you can sort of come up with your own effect. So that's kind of where they stop with this. And they do make some remarks about how, like, although Gilbreath is now fully understood because of this characterization, there are a lot of interesting variants where there is a lot to explore, especially with the polynomials that I talked about. I think there are a lot of interesting open-ended directions there, because what they talk about is, in some sense, a one-dimensional artifact. And they mention that like work on extending it to even 2 dimensions is kind of wide open. And I won't be surprised if it still is wide open. So as usual, I haven't done enough homework on state of the art, but it is a fascinating discussion in case you're interested. But I think that's where we will stop with our discussions about Gilbreath, and in tomorrow and day after, which I expect to be like the last 2 sessions of this particular reading stint, We will look at the next chapter, which is perfect shuffles, neat shuffles, and a few other kinds of shuffles. So I think I'll be very limited in my demonstration because perfect shuffles are super hard to do, and I definitely don't have the dexterity to do them. So we will just use our imagination and maybe some more JavaScript to see what perfect shuffles look like. And hopefully we'll also see some effects. So fingers crossed on that. Okay, so any parting thoughts or comments? This would be a good time. All right, so if not, then thanks so much for the wonderful discussion today. Helped me clear up a bunch of details about the structure of these Gilbreath permutations. More on other kinds of shuffles when we meet tomorrow. And most likely, logistically, day after should probably be when we wrap this up. So yeah, thanks a bunch, everyone. See you tomorrow then. Good night for now.